So hi everyone. Today we will be discussing about a very interesting and a very popular paper in NLP, that is attention is all you need, that revolves around the transformers which give birth eventually to the BERT algorithm. Now let's first of all understand what is a transformer and what is its basic architecture. So a transformer model basically helps in transforming one sequence of input into another sequence of output. Now, such problems can relate to translation from one language to another, like Hindi to English translation, Hindi to French translation, etc. Or it can also be set up for developing question answer systems, like you input a sequence, text sequence that is question, and eventually get a sequence as an answer. Basically, in a transformer, we have two major neural networks working in, that is an encoder, and the other is a decoder. So let's first of all have a brief around encoder and the brief around the architecture of decoder. Basically, the left hand side of this particular figure is our encoder and the right hand side is our decoder. So the first of all, the input sequence, assume that we are wish to translate from English to Hindi. I am a good boy becomes our input. So first layer comes is as it is an input embedding. So the raw text is converted to some embedding. Then positional encoding is getting added, multi-head. Then we have a set of four layers that gets repeated multiple times. We call this as a block. So this block has four layers that is get repeated for n number of times. Now this block has multi-head attention followed by addition and normalization, feed forward layer, and addition normalization. I will be discussing this everything in my coming up videos. Similarly, if you look towards this structure of decoder, it takes a sequence for outputs, generates an output embedding, positional encoding gets added up. Similar to encoder, it also has a repeated structure of layers that is coming in with a slight change. So in case of encoder, we have multi-head attention, add norm, feed forward, and add norm. In case of a decoder, we get two more layers, that is masked multi-head attention and add norm. So I will be discussing everything. No need to worry about. Once this block gets repeated for n number of times, we get two more layers, that is a linear layer and eventually a softmax layer. So we will be so this is a brief about transformers. So first of all, we will get started with discussing how an encoder works out in a transformer. So eventually, if you look into the zoomed image of that encoder, we have got three different sections. One is an input embedding, then a positional encoding getting added up, and then the repeated block of layers that is coming in. So we'll be discussing them one by one. So, but first of all, let's understand why we need an encoder. What is the role of an encoder in a transformer? So the role of an encoder is to decide, given the input text that we have got, which tokens in this particular text is important, right? This is what the entire idea of attention layer comes in. Attention is all you need. So it tries to provide some attention to some particular tokens coming in the sentence, so that all unnecessary tokens that are present, the model doesn't focus much on them but focuses only on the keywords that are present. How it is doing that, we'll find out soon. So first of all, we have the raw input. Assume that we have a text called as "I am a good boy." The second layer that gets added up is an input embedding. So from raw text, we need to convert these raw text into some embedding, some numerical transformation, some numerical representation. Now this can be converted by any method, word to vec, or like some other method for embedding that you know. It can The input embedding layer helps us in generating meaningful embeddings of dimension 512 for each token. So the embedding size that has been taken in the paper was 512. Now, as you remember in the diagram, after the embedding layer, input embedding layer, we have got a positional encoding layer that gets added up to the input embedding layer. If you don't, you can remember in the encoder part where we have from embedding, we add a positional encoding. So let's understand what is this and what is its requirement. So basically, let's understand the intuition behind positional encoding. Assume that we have a sentence called as "He has a black Ferrari. He also has a white cat." The second sentence being "He has a black and white Ferrari." Now, if you go with the conventional embedding methods in the input embedding layer, like word to vec or something else, so eventually, if you notice that the embedding for both black and white would be very similar, as it should be, like according to you. But comparing in the first and the second sentence, you can see that both black and white have been used in different contexts. In the first one, black has been used for Ferrari and white has been used for cat. while in case of the second sentence, both the words are used for the same entity, that is Ferrari. Now, when we go with some conventional method, this information goes missing. So there should be some difference in the embeddings between the two words, black and white. So it can be depicted that okay, they are not for the same thing and they have been used in different contexts. Similarly, if they are very close to each other, it may be the case that they are used for the same entity. Now, positional encoding helps us in achieving this only. So depending upon the position of each token that is getting used in the that is getting used in the sentence, we add up this positional encoding information into the already existing input embedding that we have generated. How it is done? Let's see that. Positional encoding: position 2i equals to sine pos upon 10,000 2i upon dimension of the model, and pos ti plus 1 equals to cos pos upon 1,000 dimension of the model. Let's understand what is this man-month formula. It's pretty easy. So for a token in the sentence, for example, I am a boy, in that we are trying to calculate the position embedding for boy, that is at the index 3. Because so in that case, position becomes 3. Now, what is I and what is I plus 1? So I is the index of the ith unit in the embedding that we've generated. So if you remember, we have generated for each token an embedding of size 512. So I represent the index of those units in the embedding 0, 1, 2, 3, 4 till 512. So for every even index in the positional encoding, we would be using this formula, and for every odd index in the positional encoding, we would be using this formula. So it's a difference of sine and cos, and eventually this will help us to generate a positional encoding for a particular token. So let's see with an example. If you see in the example, position encoding for boy, in I am a boy, so the position equals to 3. So the positional vector for the boy would look something like this. So how are positional encoding getting generated? We get the input, we got the embedding vector using some method, we add the positional vector that we have calculated above and added these two vectors, giving us the positional encoding for a given token. We will be discussing on what is multi-head attention layer that is getting used in the paper. Attention is all you need alongside the mathematics behind it. So let's get started. If you are not able to recall where it is used, so you can go back to the architecture used in the paper, where we can see that in the encoder part we have a multi-head attention layer, as well as in the decoder part as well. So first of all, let's understand what is attention and what is the requirement of attention, and how it is performed mathematically. So attention is basically a mechanism where we are trying to assign more importance to some tokens. How we are doing that? We are tweaking the token embeddings that are getting input in this particular layer, and eventually the embeddings are tweaked in such a way that important tokens in the entire sentence are automatically given more importance. They become important. The embedding gets changed a bit so that they're given more importance while learning by the model. But a question comes in that ki, can't we use LSTM or RNN? So if you remember, if you have studied a bit about basic NLP models, so memory models, so we have LSTM, RNN coming in, another sequence to sequence models. So why can't they be used? So basically the problem with these models is that they don't have a big memory storage. They might not be able to remember most of the things, but in case of attention, it is able to capture much information. It is able to store out humongous information with itself. So it is able to capture the linguistic meaning of from a particular language very easily as compared to LSTM and RNNs, because their strength for memory capacity is pretty low. Now, what is multi-head attention? So, in case of multi-head attention, what we are doing is that instead of just one attention layer, we are placing of multiple attention layers parallel to each other. So, for example, if the token embedding, the embedding of a particular token is say 20, what we are doing is that we are dividing this embedding into multiple segments and then feeding each segment to different attention layers, calling it a multi-head attention. So, it can be the case that if you have an embedding of 20, you might have a multi-head attention of 4, so that you can have four attention layers standing parallelly, where you can divide this 20 into 4 equal sections, that is 5 5 5 each, and feeding this embedding, this broken embedding to each of this parallel attention. Why we are using multi attention in place of single attention, single attention layer? Why we are using multi head attention? The reason behind that is because in a particular sentence, for example, he sat on the chair and broke it, a person can derive multiple meanings. It can be the case that the it being used in the sentence uh, here is referring to the chair. Some might say ki it may refer to he also, like in because computer again, model doesn't have a brain with itself, so it doesn't know the grammars and all that stuff. So it can be the case that it might start associating it to he, or some other attention might start associating it to the chair. So the basic idea of parallel heads coming in, the multi heads coming in, is that we can have different perspectives coming from different attention heads, and eventually we can average these all these meanings together to get to the final meaning. So that it can be the case that if out of four attention heads, it might be the case that three attention heads are indicating that it is towards the chair, while the fourth one being indicating it can be towards he also. So in that case, we will be averaging out multiple perspectives and we will be getting to a better solution. That is why we are using multiple attention heads. Uh, so let's jump into the mathematics behind how a multi-head attention layer works and how attention is provided to different tokens in a particular input that is given. So, if you remember, we have the embedding size of the input token size, the input embedding size that goes into the multi-head attention layer is n cross 512 in the research paper that has been published. Attention is all you need, where n is the total tokens in the sentence. So, for example, if we have a sentence, I am boy, and if so the input size for this particular sentence would be 4 into 512, because the embedding for each token is 512 and we have 4 tokens coming in. Now, in case of multi-head attention in the research paper, there are 8 heads for attention that has been used. Hence, this particular embedding of n cross 512 is divided into 8 parts, that is n cross 64. So we are not dividing this matrix horizontally, like some tokens are going in first head, second, some other tokens are going secondary. It's more like we're dividing this matrix vertically, so that so the embedding of each token gets divided, and the segments are getting fed to multiple attention heads. So an embedding size of n cross 512 gets divided into segments of n cross 64 and are fed to different attention layers. Now, moving on to how the attention layer works. Once we have got the input of n cross 64 for each attention head, so in attention layer we have three major concepts, that is query, key, and value. These are three entities that we are declaring: query and query weights, key and key weights, and value weights. Where query, key, and value have dimensions n cross 64. So these six entities are all n cross n matrices, where we have different dimensions coming in. For query, key, and value, the dimensions are n cross 64, similar to the segment query segment that is getting in the token embedding segment that goes inside the attention head. We need to declare a few more things: dimension of the model, that is 512; dimension of query and key vector is 64; dimension of the value vector is 64. As I told you earlier, n cross 64, and is the total number of tokens coming in. And like as I've written a note also, these numbers are just used in the paper. You can change these dimensions and you can work accordingly as well. You can have a smaller dimensions also. So there's nothing specific in the numbers coming in. Now, apart from query, key, and value matrices, we also have query weights, key weights, and value weights. So the dimension for these are dimension of the model into dimension of key, dimension of the model and dimension of key, and dimension of the model and dimension of value. So in the research paper, the dimension of these weights is 512 into 64. Okay, got it. But eventually how attention is calculated? By using this mathematical formula, that is softmax of query into key transpose upon under root of dimension of key, dk, d underscore k, that we have declared earlier, into the value matrix. So we will be running a small form, a small example, or a small sentence, and eventually see how attention is getting calculated. Assume that we have input called as Raju is good. After passing it to the tokenizer, we get 1 2 3 as an input. Now, after passing it to input embedding and positional encoding layer also, we get some embedding uh, XYZ. Okay, for this particular sentence, Raju is good. Assuming that the dimension of the model is 4. So, if you saw in the research paper, it was 512, but to demonstrate with such a huge embedding is difficult. So, what I have done is that I'm assuming the dimension of the model to be 4. And hence the embedding per token would be 4. So, it was 512 earlier. We are assuming it to be 4 for a demonstration purpose. So the output embedding layer output dimension would be 3 into 4. Pretty easy. Like total number of n is the total number of tokens, that is 3. Raju is good. Into the dimension of the model, that is 4. So assume that this is the 3 cross 4 matrix that we get after the input embedding plus the positional encoding layer after passing through these two layers. Now once we are passing it to the attention layer, assume that we have just have one head. We don't have multiple heads, else it would be confusing. So assume that we have one head, so the entire input embedding would go into just one attention head. Now again, placing out some values, dimension of key and dimension of value to be 3 and not 64 in our example, again because for demonstration purpose. And the dimension of query weights, key weights and value weights would be 4 into 3. You can go back in the blog and check out what is the reason behind it. So this is the weights that we are getting: query, key and value matrices from left and right. So this is query, this is key and this is value matrix, right? These are query weights, key weights and value weights. Let's get started. So assume that after parsing embedding layer, we have got these three embeddings for the three tokens that we got, and now we are feeding it to the embedding into the attention layer. The next step is to multiply the input embedding with the query weights, key weights and value weights respectively one by one. So the positional embedding that we have got, assume it to be the positional coding for embedding for the tokens that we have, the, that we got here, into the query weights, into the key weights and into the value weights. Now this will lead to form of this will lead to formulate query, key and value. So positional encoding into query weights gives us the query, positional encoding into key weights gives us the key, and positional embedding into value weights gives us the value matrix. So now we have got query, key and value matrix. As you can see in the structure as well, this is this input and eventually 102 011 123 222 440 282. You can see from here also we are getting these values. So each like for example, if you can see for query 102.222.213 gets is getting spreaded in this way: query 1, query 2, query 3, key 1, key 2, key 3, v1, v2, v3. Now let's start putting values in this monstrous formula. So we have got our query matrix, we have got our key matrix also. We can do a transpose for this. Dk is 3. If you remember, we have already placed that value as 3. We have assumed it to be 3. So under root of 3 we would be using, we will be doing a softmax and then multiplying by the value matrix. So I won't be going much into the formula. I will be just overviewing the values that we will getting. As d underscore k equals to 3, the root of d underscore k would be around 1.7. So I am assuming it 1 for now because for the ease of the explanation. So calculating the numerator would give us this 244 416 12 412 10, which is called as a score matrix also. Right. Now we will be applying a softmax over this resultant, as under root dk is 1, so there's no need to calculate that. Softmax over this particular token that we have, this particular matrix that we have calculated row wise. So it would be, the softmax would be along 244, then 416 12 and 412 10. I am assuming that you understand what is a softmax function. If not, you can google it out, it's pretty easy. So eventually after applying the softmax matrix, we are getting this particular matrix. So uh, multiplying by query into k transpose gives us this, and applying softmax matrix over this matrix, a softmax function over this matrix gives us this particular matrix. Now let's understand what this output means. This output means that the first token is important to the token at this particular index. So if our first token is Raj, you can see the first row in the after applying the softmax matrix, softmax function, we are getting this entry 0.01. The first row is 0.46, 0.46. It implies that importance of Raj for Raj is 0.06. For in the sentence is 0.46 and for good is 0.46, making sense. So for each token pair that can be formed, we are getting the importance value. Key for this token is how important this token is to the other tokens in the sentence. Now, the last part remaining in the attention formula is multiplying with the value matrix. If you remember, softmax qk transpose upon dk, root dk into value matrix. So, how will we doing that? If you remember, value matrix was our dimension 3 is to 3. So, we will be calculating three attention values for each token that we are getting. How are we doing that? We would be calculating these values that we have calculated 0.06, 0.046, 0.46. So each row, each unit present in the row, in this particular row, would get multiplied by each row of the value. So 0.06, as you can see in the example, into 123, 0.46 into 280, and 0.46 into 263. You need to remember the value matrix. So for each, if you like, the first row represent how important the first token is to all the other tokens in the sentence. So for each value in that particular row, we need to multiply it by the first row of value matrix, second row of value matrix, and third row of value matrix. So the first value get multiplied with the first row, the second value get multiplied with second row, the third value get multiplied with third row. I think you need to stop a bit and understand, and you just need to go back and forth so you will get it. What is actually happening. So as and when we are moving with one and one, each token pair importance is getting multiplied by a unique row in the value matrix. And finally, we will get these values for attention for input token 1, A1, A2, and A3. A1, A2, and A3. Right. Now, the last part being we need to add these three metrics, these three vectors that we have generated after multiplying with the value matrix. So after adding these three vectors, we are getting 1.9, 6.6, and 1.5. So these are rounded off. So 2, 7, 1.5 is finally the attention that we wish to calculate for the first token that we have got. Now, similarly, you can calculate the attention for the second token. You can calculate the attention for the third token. Now, in case of multi-head, if we would have multiple heads, what we would have done is that we would have concatenated these outputs. So if the output for if the output dimension is if for if for token Raj, we get this vector as a attention vector. After applying the attention layer, we are getting this output. So if we would have multiple attention heads, as of now in the example that we've used as one, so we'll be concatenating all the results together to form our to go back to our former dimension. So if you remember, if we have 512 and we divide it into 8 parts, 64, 64, 64, 64, we would be getting an output of the dimension same 64, 64, 61, and one on concatenating will again back to 512. So whatever is the input dimension would be our output dimension as well in case of multi-head dimension, in case of multi-head attention layer. So summarizing, first of all, we need to calculate QKV using the query weights, key weights, and value weights, and the input sequence embeddings. So you remember we need to multiply input sequence embeddings with query weights, key weights, and value weights. Attention matrix is getting calculated of the dimension n cross dk. Now dk is the dimension of the key matrix, if you remember. Now if we are using multi-head attention, we need to concatenate all the attention the metrics that we have generated. We will be discussing about the add norm layer that we saw in the attention, the transformer architecture after multi-head attention. So recalling the entire architecture again, you can see that after multi-head attention, we have got add a norm, again a feed forward, and again an add a norm. So let's understand what does this add a norm mean. So post-layer normalization and or add a norm refers to what happens is that we really don't wish to lose out on any particular information. So it might be the case that in the previous layer, as in when we did some operation, we lost out on some information that is present in the input layer. So to prevent that, what we are doing is whatever layer it might be in your previous layer, you need to add the input and the output of them together. So if you remember, whatever the input and the output of multi-head attention has the same dimensions. So right. Now the second step being we need to normalize this added matrix that we have got using the formula here, where gamma v minus mu upon sigma plus beta. So what does this mean? Mu is mean, sigma is standard deviation, gamma is scaling or damping factor, and beta is regularization constant. Now mu and sigma are calculated for what? They are calculated for uh, each row of the newly added matrix that we have got. So the input and output matrices that we have added up together, their mean and standard deviation for each row separately is calculated. And now the next part in the block that we saw of four layers, multi attention, then add and nor, and then was the feed forward network. So a feed forward network FFN is a pretty straightforward shallow neural network which comprises of two layers and applying a ReLU activation function. Again, after this feed forward network, we have got add norm layer, which does the same thing as we had earlier. So the entire block, if you remember, I told you that these four layers are getting repeated for n number of times. At multi-head attention, 8 heads, normalization, feed forward network, and normalization. Now it is repeated for 6 iterations in the research paper. So 6 times this particular code block, these four layers are getting repeated again and again in the model. So in like in the picture it might look a bit small in nature, but if you expand it out, so the block that are getting formed in the diagram for encoder, this gets repeated for 6 times the same attention block. So what happens is that for the first time a positional encoding goes as an input for multi attention. The next time the output of this add norm layer goes to the input of the multi attention of the second block, and similarly the add and norm output for the second block goes to the input of the multi attention of the third block, and it this process continues for 6 iterations because we are repeating the entire code blocks for 6 times. Now once iteration is done, the six times this code block is repeated, the output of the sixth block goes into the decoder now. If you remember in the architecture, there was a arrowheads that are going inside the decoder. So this is how encoder and decoder are getting connected. So what happens in an encoder, if you like, if I summarize it, so we get started with calculating input embeddings. Then we add positional vectors to format a positional embedding. Then we have a code block of multi-attention, normalization, feed-forward network, and normalization again. These four layers are getting repeated for 6 times. And once we are in the sixth block, once the calculation for sixth block are done, the output of this encoder goes to the decoder. Now we will be talking about the second half of the transformer, that is a decoder. So we have already discussed about an encoder in my previous video and like in a previous section. So you can check that out. If not, there will be a few concepts that we will be deriving directly from it and won't be explaining them again. So it'd be a good idea to go and explore that. So let's discuss about what is a decoder's role and what is its architecture, how it's working. So basically, for decoder, we are talking about while training. So we take outputs, we generate an output embedding, add the positional encoding. Then similar to an encoder where we have four layers getting repeated, here we are getting 6 layers repeated. Mask multi-head attention, add norm, mask multi-head attention, add norm, feed forward, add norm, which gets repeated again for nx number of times. So how many like whatever is n for encoder, the same number would be repeated for decoder as well, followed by linear and softmax layer. So out of this, we already know that what is a positional encoding thing. Multi attention head we have already know. Add normalization layer, feed forward, and add norm was something which was similar in encoder also. So we have already discussed it. So we would be skipping this part in this particular video. Let's first of all start from the input that is going in. The major aim of a decoder is to determine the output sequence tokens one at a time. So assume that we are working on some speech translation where we wish to convert text from English to German. Now, in that case, for this particular translation, the decoder would be using two major things. One is the attention that is coming from the encoder, whatever we have learned from the encoder, which text is more important, which tokens are important. The second thing would be the total predicted tokens as of now. Try to understand this. The decoder is predicting tokens one at a time. It is not predicting the entire sequence altogether. It is predicting the sequence tokens one at a time. So assume that we have some English sentence that we are predicting translating German. Say I am a boy, and its German translation it's I by bay. Okay, now in that case it has 4 to 5 tokens in the translation. So in that case, the decoder would be using the attention from the encoder as well as the previously predicted token. So in the first instance, in the first iteration, nothing would be predicted, right? So once we are able to predict the first token, then in the next token when we would be predicting, so we would be using the first token, the previous token, as well as the attention coming from the encoder. So we'll understand what is happening. So before feeding in the output. Let's understand what is the input that is going in a decoder for now. Because in encoder, so we have that input sentence only, but what is going in the decoder as an input? So outputs is the numerical representation of the output sequence generated, right? Which is right shifted, which is getting predicted for now. So for example, I think this is a bit confusing and we need to focus a bit on this. There are two things that would be coming uh, when we are predicting a sequence, how we are using it as an input. So what happens is that in a decoder, we are padding the entire sequence with an beginning of a sentence and an end of a sentence token, right, to determine whether sentence is ended or begin or like beginning or not. So the while predicting the first token, right, as I told you earlier, in decoder we need two things. One is attention from the encoder as well as the previously predicted tokens. Now in case of the first token, there is no previous token to use, right? So in that case, we are padding the entire sentence, the outputs, we are assuming the padding with two tokens, that is beginning of sentence and end of sentence. So for the first token we would be using beginning of sentence as an input for the decoder. So the outputs would represent beginning of a sentence token. It can be any symbol or etc. Now, once we have used this beginning of sentence token, now when we will be need to predict the first token, this beginning of sentence becomes the previous token of the output sequence. Makes sense? So the input that is going in the decoder is the previously predicted tokens. Now, if it is the first token, it is the beginning of a sentence. Token or symbol that we would be inserting. So it's sort of a padding that we're providing while fitting in while training our models, and this is what we call as right shifted. So the output sequence is getting right shifted because we are adding a new token that is beginning of sentence. So I'm assuming you must have got it. So in a decoder, it uses the information from the encoder as well as the attention that is calculated in the encoder as well as the previously predicted tokens. Now for the first token, it would be BOS. For the second token, it would be BOS and BOS, that is beginning of sentence, and the first token that is predicted using the BOS. Now for the third token, it would be BOS plus the second next two sentences, next two tokens that are predicted for the fourth one similarly. So the output, that is this output shifted, right, that is going in this attention mass attention head and this decoder is that only the previous tokens that we have predicted for now, at a particular point. Now what is masked multi-head attention? I like what I'm doing is that I'm like skipping on the part that I've already explained in encoder and the encoder part of the video, so you can watch it out. Masked multi-head attention differs slightly from multi-head attention. So in case of a decoder, if you notice, what happens is that at a particular point we don't have the future tokens with us. So for example, if you look at this example, if we wish to translate "I am good" into French, J Wise Bain, and the translation has reached Wise. That is the second token. Makes sense? So by second token, we mean that we haven't predicted the third token yet. We have predicted J, we have predicted Wise, we haven't predicted the third token. So in case of masked multi-head attention, what we are doing is that we would be masking the attention that would be calculated for Bain. So we would be assuming that the sentence is just two tokens long for now, and this is would be called as masked multi-head attention. Now it's good, like we have understood what is the input that is going in the decoder, what is masked multi-head attention. So masked multi-head attention, as I told you earlier, while training to we know ki what is the input and what is the output sentence that we're expecting. So eventually, while generating mass attention in the decoder, what we're doing is that whatever token that has not been predicted yet in the iteration, we won't be considering their attention. That is the crux of the mass multi attention. We are masking that part of the entire sequence, right? Now, the major query that remains is that how are we using the input from encoder, the output that is coming from an encoder in the decoder. So what we are doing is that in the attention layer, as we have discussed, the multi-head attention that is present in the decoder's architecture after the masked multi-head attention. What we are doing that the output of the encoder, that n cross, that matrix that we are getting for attention, we would be considering that as the key and the value matrix for this multi-head attention in the decoder. Makes sense? And the query matrix would be taken from the masked multi-head attention layer that is present previously. I think this can be a bit confusing. Try to understand this. So if you look at the architecture of a decoder in this particular point where we are heading up, multi-head attention. So in as we have discussed earlier, multi-head attention requires three things: query, key, and value. So the query and the key and the value matrices would be coming from encoder. How? The output of the encoder is taken as key and value matrix both. Right. Now we are remaining with query matrix. How we are getting that? The query matrix we are getting from masked multi-head attention. So whatever has been whatever value for query has been calculated in masked multi-head attention, we would be considering that in the multi-head attention layer as well. So eventually, if you notice, there is no training going on in multi-head attention for decoder majorly, because what is happening is it is using the pre-trained values. So the training for query has already been done in masked attention layer, and for key and value, the training has been done in the encoder part. So it is fetching the pre-trained values from the two worlds. So it is using these two things to calculate its multi-head attention in the decoder layer. So as the query vector would be available just for the scene tokens for now, predicted tokens for now, the multi-head attention layer won't be also considering the future tokens while calculating the attention for the tokens. So for example, the rest of the code pretty easy, where we have got a normalization layer, feed forward layer, normalization layer that I've already explained in my previous videos as well in this video in the encoder part. So the entire code block that is getting repeated in a decoder is masked multi-head attention plus normalization, multi-head attention plus normalization, and feed-forward network plus normalization. Six layers are getting repeated for 6 times. After this code blocks is repeated for sixth time, we have got two more layers. One is a linear layer followed by a soft max function. Now this soft max functions gives us the probability for the most suitable token that should be followed in the output sequence that we have. Now once we are able to get this particular new token, okay, this is the next token that we have forecasted for, that we have predicted for the output sequence. That particular token is considered in the output, that if you remember, and for the prediction of the next token, this token would also be considered in the input that is getting considered for the decoder, right? So if you look at this, the current team of decoder is to predict the third token of the output. Once the third token is predicted, it goes to the tail of the output sequence and a new iteration starts. So there are multiple iterations going on. So once you are able to predict a new token, that token goes back into the chain, and eventually, when you are trying to predict the fourth token, this third token is already being considered in the attention layers now, because now the decoder has already know key, okay, this is the token that I have, this is the token is seen for me. This is no longer a future token for me. Similarly, until and unless this iteration goes on, until and unless an end of sentence token is predicted by the model, determining ki, okay, the sequence ends here. So if the end of the sentence token doesn't get predicted, the iteration for prediction goes on and on, predicting one token at a time. And once we are able to get the once we hit the end of sentence prediction, token prediction, we stop there.